Okay, yeah. So yeah, I just want to start off. So thanks for the invitation to speak here. It's very nice to sort of have a break from the quarantine, so to speak. um, and I do a little bit of apologize in advance because I had agreed to give two talks, and I accidentally sort of they wanted they wanted me to talk about the same thing, but both are actually sort of quote unquote in Shanghai, and the other one is next week. So hopefully. You know, hopefully there won't be too much repetition. So I'm going to talk about some work that are being done with Alex Blumenthal, who is a postdoc at University of Maryland, who will be moving to Georgia Tech in the fall, and Sam Punshon-Smith, who was a graduate student at Maryland and is now a postdoc at Brown University. Right. So we're going to start off with what is turbulence. And so we just had an extremely beautiful talk by Charles on weak turbulence, which is one regime of a sort of much larger set of phenomena that physicists refer to as turbulent, and sort of like always will be like weakly dissipative. Now, of course, Charles was talking about the sort of the ideal limit of there is no dissipation at all. I'm working sort of slightly different regime, as I'll explain. But it always occurs in sort of weakly dissipative, where the dissipation is basically negligible, more or less. Infinite dimensional, that's key. Systems which all share some unifying properties we're not going to get too much into, but it comes up a lot in fluid mechanics and plasma physics, and both in kinetic and in hydrodynamic plasmas, and also as we saw in nonlinear dispersive equations. And so there's a lot of key features that sort of go through all of these. And so one is chaos, and I'll explain what a Lyapunov exponent is later because I will be discussing them. And essentially what it means is if you freeze all of the other parameters in the system except for the initial condition, then the two trajectories in phase space will separate exponentially fast. And so this is what is meant by chaos. Now this is not an infinite dimensional phenomenon. So this is not what characterizes turbulence. So one of the other major things that is in all sort of quote unquote turbulent systems is the formation of multiple scales. And I don't mean like one or two scales. I mean it forms a continuum of scales. In many examples, it starts creates a continuum of scales between large scales and small scales. But actually, in many systems, it creates continuous scales also from sort of order 1 scales to very large scales. So it can go both directions. And this is sort of in the limit of weak dissipation. So the sort of regime that I'm studying is actually going to be where you send time to infinity first, and then you send the dissipation parameters to 0. So this is, so you sort of send time to infinity, reach a kind of statistical steady state, which I'll explain rigorously, and then sort of study singular limits of this. It's a different regime than what was discussed in the last talk. So this is first thing you do is send time to infinity. And this is what is most common in experiments and in a lot of physical settings. So it's a very common and important regime. It's not the only one. So both types of studies are important physically. Another hallmark of turbulence that's very important is the concept of universality. So what you see is that in these small scales that are being created by the nonlinearity, the statistics in between the large scales and the small scales seem to be universal. So, for example, if you're looking at the wake of a car, the flow of the fluid past the car is extremely complicated. But what universality is suggesting is that the small scales smaller than that of the car. It shouldn't really matter if it's the wake of a Lamborghini or a Honda Civic, aside from the sort of total amount of kinetic energy available. And so there should be a range of universality, and this is called the inertial range in fluid mechanics, at least. Okay, so how do we start? So like, let's say we want to sit down and we want to prove these universality laws in turbulent systems. So this work actually started from basically a bunch of us, some postdocs and grad students, and we sat down and we wanted to understand turbulence. And we just started reading physics papers and physics textbooks. And so we went around and we wanted to find the simplest system that really models something in the real world. So not a toy model, but the simplest system that models something that physicists actually use, for which we could prove a universality law. And I'm quite convinced that we have found this system. So the system is called passive scalar turbulence. And so what you do, it's not obviously simple at first, but I'll explain. So what you do is you solve the Navier-Stokes equations. And so here we're setting time to infinity first before we do anything else. So you need to have an external driving force that does not disappear. So F is deterministic. We don't care. It's not important. That it's not going to play a major role. What's going to play the big role is the stochastic forcing here. For purposes of this talk, I will focus on White and time stochastic forcing. You have some flexibility on that, which I won't discuss. And so this is a stochastic, and I'll also discuss why we take stochastic forcing. And then so you solve the Navier-Stokes equations, and then you also dump a passive scalar. So G is a scalar field that's being dumped in, added randomly, sort of constantly, and it's being stirred up by the fluid. So it's being advected, and it has its own diffusivity there. And you should think of this as like a small temperature variation or a small salinity variation, variations that are small enough so that it doesn't really have an important effect on the fluid. So it's an approximation, of course. And then what you want to understand, so passive scalar turbulence, what they call passive scalar turbulence, is the regime kappa going to 0. So this diffusivity parameter going to 0. Okay, so let me show you what's expected. Okay. So first I want to say, like, what is the fundamental physical quantity that we're interested in studying? So the most basic question that physicists would ask is, how does energy distribute itself through this quote unquote inertial range? So through this range of universality. And so, for example, in the fluid, you might want to study how the kinetic energy, so this is again the Fourier transform, this is how the kinetic energy distributes itself in frequency. And for the passive scalar, we're going to study how the L2 density, which you can think of as a scalar energy, distribute itself in frequency. And so these quantities are normally called power spectra by physicists. And what's expected is that they are power laws, actually, and that these power laws are universal. So that in the inertial range, you just get some particular numbers here that don't depend on the experiment. So you see that the solution should actually become very rough. So that's a hallmark of turbulence. And that the roughness is independent of the external forcing. So this is what's expected of passive scalar turbulence in the regime when the diffusivity of the scalar is much less than the viscosity of the fluid. And so this is just a schematic. I'll show you some experiments. So this is a log-log plot of the power spectra in 3D. So this is for 3D fluids. 3D fluid mechanics is a little simpler than 2D when discussing turbulence for reasons I'm not going to talk about right now. And so there are basically 3 regimes that you observe in experiments. One regime is the regime of no universality. So the specific structure of these curves just depend on the specific choices of your random fields. Okay, so that's not particularly interesting. There's no universal theory for that. All you can do is solve it with a computer or run an experiment. Then what you have is you have the inertial range of the Navier-Stokes equations, which is observed. So the power spectrum for Navier-Stokes in 3 dimensions is observed to be pretty close to -5/3. So this was a key prediction of Kolmogorov in the 1940s. And what's expected is that what's observed is that the passive scalar power spectrum actually matches that of the fluid. This is called the Abkov-Corson regime. We're not going to do that, as I'll explain. Then the inertial range of the fluid ends after the dissipation takes over. But then if nu is much bigger than kappa, then you'll have another regime where the diffusivity of the scalar has not taken over. And so you still have some kind of universality regime, a sort of different inertial range of the scalar. And so what we're going to be able to study rigorously is this regime. Here, we do not have a theory for what this regime is, and where this line is, we don't know. Of course, thinking about it, you see that, yes, in order to understand that regime, you would have to first understand hydrodynamic turbulence in 3D Navier-Stokes quite well, actually. That would be the expectation. So, of course, we have not done that yet because we're trying to start with the simplest thing. And so we don't know what's going to happen in this regime. All we're going to be able to understand is this regime. So that's our purpose. It's called the Batchelor regime. And in 1959, Batchelor predicted a power law of the scalar to be -1. And then, of course, it's not too hard to guess that that power spectrum will cut off at around kappa around frequency like kappa to the -1/2 because of parabolic regularity here. And so that's what we're going to prove actually for the system. Going to identify this regime. So if you look at it, so of course, like physicists and engineers really care a lot about what the power spectrum is. And so they did a lot of experiments on this, still occasionally do experiments on this. So this is an experiment. It's actually not an experiment, it's a natural observation. So they just drove a ship through the ocean and dumped some sensors over the side of the boat, and they measured temperature variations in the ocean. And so this plot is just experimental data. So here is the power spectrum of the fluid. So this, you can see the -5/3 power spectrum, and then it cuts off. And here you can see, of course, in experiments, the schematic of where the inertial ranges begin and end is a lot more fuzzier in reality than on this sort of idealization. But it's still the same idea. You have a matching slope in the scalar here, and then it levels off to the -1 Batchelor regime. This is a controlled laboratory experiment. This is a salinity variation. And again, it's the same sort of plot. This bottom line is the velocity, and this top line is the passive scalar. And there you see it matches Batchelor's theory fairly well. This is a conglomeration of computer simulations done in 2003. So once people started to have computers powerful enough to ask this kind of question, this is just the Batchelor regime. So the other regime is not being studied in this. Okay, so this is just the Batchelor regime, and you see, again, almost all the computer simulations match Batchelor's prediction, except for this kind of weird outlier, which I have no idea what's going on with that. And so this is what this area of the regime is what we want to capture. All right, so when thinking about this, the first thing you have to ask is why -1? So why is Batchelor's law that prediction? And that's an important thing to understand, because that's what we're going to be trying to prove. And so the simplest toy model we can come up with that correctly captures y -1, but it's a little deeper than how Batchelor guessed -1, is the following. So what we're going to do is we're going to replace the advection by Navier-Stokes. So the nonlinearity, which is creating the turbulence, so to speak, is this transport, as we'll explain. So it's not the nonlinearity in Navier-Stokes. That is actually not particularly important for this particular regime of passive scalar turbulence. So we want to replace this sort of transport by Navier-Stokes by the vector field with instead some very simple transport. So we're going to use Arnold's cat map. So this is an automorphism of the torus. So you just identify the torus with the unit square. You map it forward with this matrix, this hyperbolic matrix, and then you wrap that back onto the torus. And it's well known that iterations of this cat map are uniformly hyperbolic. So orbits separate exponentially fast, and it's a really strongly mixing iterative map. And I'll explain what mixing is soon. And so this is going to be our toy model for statistical stationary passive scalar turbulence. So let's forget about the dissipation. We think that that's not so important. And so each time step, we're going to dump in a random amount of passive scalar. So these omegas are just IID Gaussian random variables, and it's occurring at order 1 frequencies. So we just dump it in at the lowest frequency in the system. And then each time step, we're going to map forward by the cat map. Now the cat map, because because of the special property of the cat map, it maps Fourier modes to Fourier modes. So you can explicitly solve this iteration, and the answer is this. And if you look at this, you say, okay, well, A inverse transpose has one eigenvalue which is bigger than 1 and one eigenvalue which is less than 1, because it's a hyperbolic matrix of that type. And and you can check that the eigenspace is sort of not lined up incorrectly. So this vector lives at around scale lambda to the power j. And so what's going on here is that each term in this frequency lives at a sort of different lambda-adic frequency. So it's like there's one term that lives at lambda, another term that lives at lambda squared, in other terms, it looks at lambda cubed. So it's a random Fourier series, which has just one term in each lambda-adic shell. And that one term in each lambda-adic shell has about order 1 energy in it. So because this is just a variance 1 Gaussian random variable. So each lambda-adic shell has about order 1 energy. So this is the prediction that you get. Each lambda-adic shell has order 1 energy. And that's exactly actually Batchelor's prediction, because Batchelor predicted, Batchelor made this specific prediction, 1 over k to the dimension, actually. So remember, physicists move the surface area of the unit sphere into the power spectrum to sort of normalize that. But that's one way of reading Batchelor's prediction, is that you have about 1 over k to the dimension in every Fourier mode. And so if you average that over geometric frequency shells, this is the same prediction. Now, Batchelor's toy model was actually even simpler and was similarly sort of only supported in 1 Fourier mode. And so, Batchelor's prediction also doesn't really explain why you should see it in every frequency, though that's an interesting question. And yeah, as you'll see, we'll also have averaging in our answer. So there's still future research in figuring out if it really should be true point-wise in frequency in general. For this model, of course, it is not. Okay, so now what we want to do is we want to replace this very simple cat map iteration with stochastically forced Navier-Stokes. And so let us set a framework. So the 2D Navier-Stokes equations, it's more or less the most difficult case that we can study. So we can also study 3D in T3 if you replace the viscosity with hyperviscosity. And that case is not really any harder or easier than the 2D case. It's just slightly different. And so let me not discuss that and just discuss the 2D Navier-Stokes equations. And so we're going to subject it to a White-in-time divergence-free forcing. And we're actually going to force every frequency, or at least all sufficiently high frequencies. So there's definitely future research to get a wider range of possible forces. And we're going to just fix things simply. We're going to force that every frequency has forced with this particular power law, and alpha has to be big. Okay, so alpha can be anything that isn't too small, essentially. So it's not that we have a condition that alpha needs to be small. So alpha actually needs to be large, and it actually makes sense, because if you have forcing that's acting at small scales, then this picture becomes false, right? If your forcing is doing something a lot here, then the fluid is going to be doing something which would create this, which would create a different power spectrum. So when asking these universality questions, you have to work with smooth enough forces. How smooth is smooth enough? I don't know, of course. Okay, now this stochastic PD is extremely well behaved, very well studied. So it defines basically as good of a random dynamical system as you could hope for on a phase space of Sobolev regular vector fields. And it defines a Markov semigroup. So this is an important evolution which tells you how to evolve statistics. So phi is an observable. So it's a question you would ask about a Sobolev regular vector field. And then what PT phi is saying, if I know what the state of the fluid at time 0, then PT phi is the expected value of this statistical observation at a future time t. Okay. And it's very well known, very classical by now, that there exists a unique stationary measure for Navier-Stokes, which means that if you randomize the initial condition with this stationary measure, then the statistics don't change. Okay. That's what it means to be a stationary measure. So each individual trajectory, of course, is changing a lot, but the statistics are not changing. So what you should have in mind is like the wake of a fluid behind a stone. So if you just go look at water going over a stone in a river, that is what a statistical stationary solution looks like. And so like the wake of most moving vehicles, if you throw a baseball, the wake of a baseball, things like that. That is what statistical stationary solutions look like. So they're of course not stationary, but the statistics are stationary. And you can check, and so of course by the ergodic theorem, you only need to run one experiment and just look at it long enough, of course. So that's one thing to note about this stationary measure, because it's unique. Okay, but now, right, so that's about the fluid. So that's all been pretty much solved in the case when we're talking about the torus. That's pretty much solved all those questions. And so now what we want to understand is the motion of the scalar. And so for this, we're going to use the Lagrangian flow map. So this is asking if I have like a little dust particle in the fluid, I want to know where it travels as a function of time. And so it just solves this random ODE given by the velocity field. Note, this is not a Markov process. This is not a stochastic differential equation. So phi tx, the motion of a single particle it's not a stochastic diffeomorphism, if we know this definition. So it's just a diffeomorphism of the torus. Okay, so now the first question we want to understand. So we want to make it look like the cat map, and for reasons which are not immediately obvious, it actually turns out that we are dead in the water if we cannot prove that this flow map has a positive Lyapunov exponent. So a positive Lyapunov exponent is in some sense the weakest characterization of chaos that one could hope for, and we actually need a very strong characterization of chaos in the end. And so we need a positive Lyapunov exponent to do anything. And so what is a Lyapunov exponent? So there's a very beautiful ergodic theorem. If you've never heard of it, I definitely suggest you look it up, called the multiplicative ergodic theorem, which actually tells you a lot of things, which I'm going to sweep under the rug. But one of the things it tells you is that there at least exists, under very mild conditions, there exists a definite Lyapunov exponent. So essentially, just from well-posedness and basic regularity properties of the stochastic Navier-Stokes, there are positive, sorry, you don't know they're positive. There are Lyapunov exponents. So there are asymptotic growth rates for the gradient of the vector, for the gradient of the flow map. So this tells you, as time goes to infinity, the asymptotic separation rate of two particles that start very close together. And so what you want to know is that this Lyapunov exponent is positive. That's the goal. Unfortunately, and so this is what we call chaos, or what I'm going to call chaos. Unfortunately, this is actually, for most systems, is extremely hard. So for deterministic systems, if you know dynamical systems, you realize that except for very simple systems like uniformly hyperbolic maps, this is essentially impossible. You know, maybe you know that there exists lots of systems with positive Lyapunov exponents, but there is no real general known technique to tell you, if I give you a system, you can't tell me if it has Lyapunov exponent or not, or positive Lyapunov exponent or not. The MET might tell you that there are Lyapunov exponents, but knowing that they're positive is a much different proposition. And so, and for random systems, the situation is a little better, and as we'll see, good enough for us. And so this is what we want to understand. And it's very important to understand that this is chaos of the Lagrangian flow. This is absolutely not the same thing, and is in fact a priori unrelated to chaos of the velocity field in its infinite dimensional phase space. So physicists make a distinction. This is what's called Lagrangian chaos. And the other one is what's called Eulerian chaos, for which there is no notable progress mathematical on. No notable mathematical progress on proving Eulerian chaos. But Lagrangian chaos we're going to be able to handle. And it's easy to come up with examples of vector fields which have Lagrangian chaos, but not Eulerian chaos, but also vice versa. You know, it's not, they're not a priori the same thing or anything like that. So just get that out of your head now. So Lagrangian chaos is what we're interested in, not the butterfly effect for the infinite dimensional phase space of Navier-Stokes. Okay. And in fact, as we'll see, the case, so what we expect is that nu small is necessary for Eulerian chaos. But that's not true about Lagrangian chaos. So as we'll see, nu small is actually the hard case for proving Lagrangian chaos, for reasons I'll explain next. So if you have no nonlinearity, then the Navier-Stokes equations would reduce to, they're called the Stokes equations, which is basically just stochastic heat equation. And so for example, if you just force 4 modes of the stochastic heat equation, you would get this evolution. So this very simple, very smooth vector field. The coefficients are Ornstein-Uhlenbeck processes. and all independent. Oh, sorry. I guess I realized I can't see if anyone asked a question. I don't know where my chat box went. So if someone asks a question, maybe you'll have to say it out loud because I can't. For some reason, Zoom is hiding from me if you say anything. Just so you know. So I haven't seen any of your chats if anyone asked a question. So please feel free to interrupt me if I'm going too fast or anything like that. Right. So let's talk about this velocity field. So so actually, if you think about this velocity field, just heuristically at least, you kind of think of it as, okay, there's sort of like 4 shear flows. Sort of one shear flow that kind of looks like this, and the other shear flow kind of looks like this. And then like phase shifts of these 2 shear flows actually is what you should think of it. And so it kind of looks just like, maybe looks like the random composition of, it looks like the composition of random shear flows, which are transverse. But transverse shear flows are hyperbolic. So the cat map, which is sort of like our toy model of uniform hyperbolicity, is just 2 transverse shear flows, in fact. And so this velocity field should be sort of, the orbits should be very hyperbolic unless the z's are somehow chosen in a very degenerate way. And so the important thing to understand is, I cannot emphasize this enough, is that in measure preserving systems, which are, for example, in our case, that means incompressibility, chaos is what you should expect. In order for something not to be chaotic, you need some deep degeneracy. The difficulty is that in deterministic systems, we have no tools for ruling out that kind of degeneracy. And in random systems, we have more than 0, but not that many, but more than 0. And so that's the key. So the point is, for this system, for this simple vector field, random shear flows should basically always, these kind of like random transverse shear flows should always be chaotic, because in order for something not to be chaotic, the z's have to line up in a very pathological way. And so stochasticity allows you to sort of cut out the abnormal pathologies that may or may not be present. Well, in deterministic dynamics, they are present. They're known to be present in deterministic dynamics. But in stochastic dynamics, they are not. So what is the enemy when you turn on the nonlinearity? Of course, in the nonlinearity, now these z's are correlated. And of course, you also have many more. You have infinitely many now. And moreover, when viscosity is small, incompressible fluids spontaneously like to form vortices. So this is a picture of stochastically forced Navier-Stokes in a periodic box made by physicists. And the field that you were looking at is vorticity. But the important thing to know is that it's basically solves a scalar evolution equation. It's not a passive scalar, but the vorticity itself solves scalar transform. And so what you see here is that they're clumping into vortices. So what's going on here is that the flow lines are all sort of closed ellipses, at least if you freeze this picture for a second. And inside an ellipse, of course, the gradient of the flow map is not growing exponentially. So this particle and this particle are separating only linearly fast, which is not fast enough to have a positive Lyapunov exponent. And so you have kind of like pockets of elliptic dynamics where you're supposed to have sort of hyperbolicity. And we know, if you're familiar with dynamics, that this creates huge problems in deterministic dynamics. It's sort of one of the fundamental reasons why even systems which look hyperbolic mostly, it's still impossible or unknown yet how to prove positive Lyapunov exponents. And so this is kind of our enemy. Nevertheless, with stochastic forcing, we can prove that, well, this won't stop us, essentially. And so this is the theorem statement. So for all values of the viscosity, there exists a deterministic lambda, which is our top Lyapunov exponent. And it's very important to understand that this same asymptotic growth rate is achieved for all particles and all initial velocity fields in our phase space almost surely. So it's not like some weird trick of random averaging or something like that. It's every time you run the experiment, any particular particle you look at, you will always measure this same lambda. The fact that lambda is deterministic is actually an ergodic theory thing. But it's important to understand this is what I mean by positive Lyapunov exponent. So it's not, if you try to characterize it another way, maybe you won't successfully characterize actual chaos. So it's really saying if you just vary the location of the particle and freeze everything else, you'll see the exponential separation almost surely. Okay, and so what this tells you about Navier-Stokes, for example, is that this kind of these elliptical vortices, of course, they merge, they break apart, and they do all kinds of stuff, and somehow in the middle of all that dancing and merging, they cannot somehow trap a chunk of fluid in them forever, so that they only have a zero Lyapunov exponent. So every particle experiences the hyperbolicity. Okay, and just as the previous heuristics should suggest, if you have no nonlinearity, the proof is much easier. And so if you study this vector field, so the theorem applies in this case, and many other, where the phase space is finite dimensional, it's much easier. Yeah, linear finite dimensional is the easiest. Okay, so, but this isn't good enough. So this what tells you is that individual particles separate exponentially fast. But this is not good enough for Batchelor's law. And so for this, what we need is a concept called mixing. And a lot of mathematicians have been studying this recently, so it's a lot of good work going on. And but let me just explain the concept. So mixing is a global property. So here I have, this is from the website of Jacques Finest, who's an applied mathematician who studies mixing. And mixing is, when someone who studies fluid mechanics says mixing, they literally mean the state type of mixing, like mixing milk into coffee. It's not an abstract mathematical concept. It's just regular mixing. And so when I say I want to mix this fluid, I want to turn this white in a weak sense, at least, just by stirring it up. And you see this is a global property, right? Because in order to turn this white, I need to kind of transfer all the red here and all the blue here everywhere. So it's a global property rather than a local hyperbolicity. So and of course there exists in dynamics, there exists tons of examples where you have positive Lyapunov exponents, but for which this global mixing is not exponential. So we need to rule out that pathology next. Okay, so how do you quantify? So let's just think about mixing, so let's think about the initial value problem and just mixing a scalar. And actually let's first just forget about this term for a second. So you just want to mix what I would call an inviscid scalar. So the most classical way to quantify mixing is with a negative sublove norm decay. There's a great paper by Jean-Luc Tuffaut who explains why this is sort of a very good way of measuring mixing. It's not the only way. I'm not going to discuss it further. What we want to prove is something like this, that exponentially, the scalar decays in h-1, exponentially fast. And we see by the definition of this negative sublove norm, that means all of the information has to go to high frequencies exponentially fast. Positive Lyapunov exponents just says maybe you have to form some small scales somewhere. But this tells you that everything has to be going to small scales exponentially fast. That is our goal. Now, by the duality characterization of sublove spaces, you can also check that you can relate this negative sublove norm decay directly to the flow map. Because what you're going to do is you want to prove exponential decay of these kind of correlations of the flow map. And so this is exactly, so what we want to prove, and this is what we eventually prove, is that this is true. Okay. And so what you want to prove is that you want to have these exponential decay of correlations. And we want this, again, to hold almost surely. It's not, we don't want to randomize this. We want it to hold almost surely. Otherwise, it's not relevant to proving turbulent behaviors. Okay, so the next theorem, I'm just going to compress the results into one sort of small theorem. So what we need is that this mixing happens exponentially, happens almost surely, and it happens independent of kappa. So the inclusion of the diffusivity isn't allowed to slow down the mixing. So this isn't allowed to slow down the mixing. Okay, so what do we have? So there's a parameter p, which is going to be, well, we'll see what it means. And then for each p, and also this holds for all nu, of course, there exists, again, a deterministic rate gamma, which is independent of the diffusivity kappa, such that this holds, and d is a random constant that does not depend on g, and it does not, so a priori it actually does depend on kappa, but it's uniformly bounded in kappa. So there's a small subtlety there. So what I mean by this is that moments of d, which is where p comes in, are controlled uniformly in kappa depending only on the initial condition of the velocity field, the initial state of the fluid. And so d, you should think of log d as a random waiting time of how long you have to wait until you see the mixing, as we can see here. Right. So before that time scale, this won't give you any decay. And so you really need, so log d is like a time scale. It's like a waiting time. Okay, so it's actually not too hard. It's not completely obvious, but it's not too hard to check that this is qualitatively sharp in the sense that this lower bound is true if you just change gamma d and gamma. And that's true no matter what. So that's not a dynamics thing. That's just a parabolic regularity thing. Well, okay, not a parabolic regularity thing. That's a, it's parabolic regularity for the Navier-Stokes equations together with basically regularity of transport equations. You can prove this lower bound. You know, with the same thing with a gamma deterministic and d random with this bound. Okay. Right, and so let me just loop around real quick and explain just real briefly its relevance to passive scalar turbulence and what we can prove there. So this is the passive scalar turbulence system. I'm going to simplify my life. I'm just going to pick one smooth function to force in the scalar. It's again by very well-known techniques I'm not going to discuss. You can prove that this Markov process has a unique stationary measure, which we're going to call mu kappa. And the turbulence problem is again to study the singular limits of this measure as kappa goes to 0. So again, you send time to infinity first, and then you send kappa to 0. Okay, and I'm going to refer to ensemble averages of this measure as this notation. And so this is Batchelor's law, but now averaged over balls. So what it says is that there is some n0, and this is the start of the Batchelor regime. So it's independent of kappa. It does depend on nu in ways, obviously, which we do not understand. So it depends on, it's n0 is deterministic, but it depends on the shape of the force, I should say. It depends on the shape of the forcing in nu, but it's deterministic, which is kind of clear from the statement, but which says, so in this range of scales in the Batchelor regime, you can upper and lower bound this spherically averaged Batchelor's law, the spherically averaged power spectrum. And so this scales above and below by log n, exactly how Batchelor predicted, but you have to average over balls in our current proof. Now this is, a priori, it's kind of like a regularity estimate, both upper and lower regularity estimate. And attaching it with some simpler arguments to control things for larger frequencies and things like that, you can actually produce enough a priori estimates to pass to the limit to the inviscid problem. And what you get is a stationary solution of the inviscid problem, so no diffusivity at all. And of course, that's deeply pathological because you have a priori conservative equation, B is smooth, U is pretty smooth, and yet you're violating all the conservation laws because you're in statistical stationarity, but you're dumping in energy constantly. And so what you can prove is that you have a non-vanishing scalar energy flux through all scales. So this is what you can prove in the limit. So this converges to a number, like a fixed number, as nu n goes to infinity. Well, I mean, it converges to L2 norm of B. And so sort of you have energy flux, constant, basically asymptotically constant energy flux all the way down. And that is something that should be true about every turbulent regime that you study. that you should have a sort of constant flux of conservation laws through the inertial range asymptotically. And you have the Batchelor spectrum all the way down. So the solution is clearly not an L2, but in fact, you can prove that the solution is not a function at all, essentially. It's not even in L1. Basically because L1 is also a conservation law, and it also would need to be violated, roughly speaking. Okay, so this is kind of thing where you can really pass to the limit and construct stationary solutions to the forced inviscid problem. This is kind of like the dream for Navier-Stokes, for example. But okay, that's still far away, but this is for the simpler passive scalar turbulence problem. So that's what we are able to do. Actually, I'm going to skip this slide. Basically, the key, I do want to discuss one thing. Of this slide, it's the upper bound that's the hard one. So you would think, and when we first think about it, we thought it was the lower bound, but it's actually not. So the upper bound is where you actually use dynamical systems, and the lower bound is where you use, again, sort of the parabolic regularity kind of statements. So why? So if you think about, so let's think about this scalar. So I'm going to let ST be the 2-time propagator for this equation, which is linear in G. Then my statistics, if I just look at frequency shells less than or equal to n, by Ito isometry, I can relate it to this 2-time propagator like this. And so you see actually the upper bound is about understanding how quickly this propagator can evacuate frequencies from can send information from low frequencies to high frequencies. And that's where you need the mixing results. That's where you need dynamical systems. The lower bound is just saying that it can't evacuate those frequencies like arbitrarily fast. So the lower bound is sort of a regularity statement, just a basic a priori regularity estimate, essentially. And the upper bound is where you actually need to use dynamics and dynamical systems. It's the upper bound that's the hard thing, harder thing. The lower bound is not trivial, actually. So these things where you use parabolic regularity and stuff like that, that's actually not easy. I'm just, yeah, especially for these stochastic systems where the velocity field is not exactly bounded uniformly in time and stuff like that. They can undergo fluctuations and things. It starts to get complicated, but it's definitely much more work to do the dynamics to get the upper bound. Okay, so let's talk about the dynamics. And so I've sort of hinted at this, but I want to emphasize it, is that the proofs are based on random dynamical systems and stochastic PDEs. So Alex Blumenthal, one of the collaborators, is an expert in random dynamics. He was a student of Young, and he basically taught Sam and I how to do random dynamical systems so that we could solve this problem. And so let me just impart to you the most important fundamental of dynamical systems that we use. And this is a key idea of Furstenberg. And this goes back to the question of how do you actually prove that you have a positive Lyapunov exponent? Because this is, in some sense, an extremely difficult problem in general. And so why can we succeed even though we're studying actual fluid mechanics equations? And so this idea, introduced by Furstenberg in the 60s, let me explain it for IID random matrix multiplication. So what I'm going to do, and it's very important, determinant 1 matrices, 2 by 2 for now. And I'm just going to look at these random matrix multiples. And I want to ask, when do they grow? When does this random matrix multiple grow exponentially? So when does it stretch vectors exponentially fast? Like this. And so it's actually easy to come up with 3 examples where it does not happen. So one example, of course, is where every matrix is just a random rotation. Then there's no exponential stretching at all. And so that's, okay, so that makes sense. So then the answer, eta is equal to 0. Then let me give you another example where every matrix is a random shear flow, but all aligned with one another. So let's say maybe alpha is random, but they're like this. This will also, it will stretch vectors, but only polynomially fast, some power of n. So also 0 Lyapunov exponent. The other example is, the last example is this one, which basically what you have is that you have exponential stretching, but then every so often you flip the vectors that are being stretched now get flipped to become vectors that are being compressed. So you flip the stable and unstable directions. And so this also does not grow exponentially. It grows like something like e to the square root of n, which you can kind of guess forward. And so what Furstenberg proved in the 60s is that these are the only counterexamples, which I find a really staggering rigidity result. It uses the algebraic structure of SL2. So, and well, SLD in general. Basically, he tells you that if the Lyapunov exponent is 0, then either there is a deterministic inner product for which you're almost surely in isometry, so that's the random rotation case, or you have 1 or 2 lines such that these 1 or 2 lines are deterministically mapped back and forth from each other. And these lines are deterministic. And so you see the shear flow is the case of 1 line, and this is the case of 2 lines. And those are the only examples up to change of variables. And so the general principle is that in order for Lyapunov exponent to be 0, you need an almost surely invariant structure. So you need to somehow reduce your dynamical system, your random dynamical system, into a deterministic dynamical system in some sense or another. And so this is a really deep observation that really makes rigorous this idea that chaos is the generic dynamics, and you need pathology to be unchaotic, as long as you're in SL2 or SLD, something volume preserving. Our system is obviously much more complicated. So let me just introduce some Markov processes real quick, although I see I'm sort of running out of time, but that's okay. What I want to do is there's gonna be 2 main Markov processes that we want to study for this first, this Lagrangian chaos result. The first one is I want to study the evolution of a single particle, but that's not a Markov process. So I actually have to study the joint distribution of velocity and particle. And that is an infinite dimensional Markov process. Then on top of that, I want to understand stretching and compression in the flow map locally around this particle. And so what I'm going to do, this is a classic trick in dynamical systems. What I want to do is I want to study the projectivized evolution of a vector under the gradient of the flow map. So I want to study this evolving linear subspace. And the point is that this V will tilt into the directions where there's a lot of stretching, but XV lives on a compact manifold, right? It lives on the projected bundle of the torus. And so the one step is to prove that this guy has a stationary measure, a unique stationary measure. Technical step, but yeah. And so by combining some ideas from dynamical systems in the 80s and sort of like the late 80s, roughly speaking, you can prove that if the Lagrangian chaos exponent, so if the Lagrangian Lyapunov exponent was 0, then you have to be in these 2 dichotomous regimes again. Either there's a deterministic family of inner products, but now it depends on U and X, it depends on this phase space, such that this gradient of the flow map always maps as an isometry from one to the other. Or there's a deterministic family of lines that depends again on the position, on the location in phase space, that is always deterministically mapped by the gradient of the flow map. And it's very important that everything varies continuously with respect to its parameters, and that these guys are deterministic. And you see, so this rigidity theorem basically tells you that in order for there to be a 0 Lyapunov exponent, what would happen is that if you knew where the ux went, then you would know basically what this does. And so you need to rule that out. You need to show examples of u and x's where you know u and x, but for where this probability distribution is fairly random still. And so what you need to know is that even if you condition, so if you think about this process, even if you condition on the endpoints, you need to know that this still is kind of non-degenerate. Doing that actually is, it's actually fun. So it sounds like it's going to be hard, but it's actually more fun than it is hard once you really know what you have to do. You just have to come up with some examples for which this is true, right? Because you don't need to prove it for all pairs of u and x. You just need to come up with examples of u and x for which this is true. Again, because of this deep degeneracy that's required. And you could basically turn it into an approximate control game because you only need positive probability events So by some stability theorem, you can just demonstrate, okay, I found a deterministic control that does it, and therefore there exists random controls that are close enough. And then you just use basically the fact that these flows are exact solutions of Euler. And so the presence of the nonlinearity basically doesn't matter as long as you're only forcing on these modes. And then you play a game of saying that translations, so shifts and translations of these basic fundamental flows on the torus can produce flow maps that have enough richness to them to violate Furstenberg rigidity. And that's positive Lyapunov exponents. Okay, to prove exponential mixing, it's a long story and I'm out of time. Essentially, you have to study, let me just give you the intuition. The intuition makes sense. You have to study the motion of two particles at the same time. Because you're studying correlations. So you have to study where two particles go. And in the end, it's going to be, the whole point is to prove that these two particles, when they get close together, which they always will infinitely many times, they have to separate again exponentially fast. And so you're going to use the positive Lyapunov exponent. You have to sort of justify a linearization. So when the two particles get close together, you have to justify that they separate again exponentially fast, sort of uniformly kind of in time, essentially, up to some fluctuations. And then, okay, it's a lot of work, but it's essentially about justifying a linearization and doing a lot of spectral theory of Markov processes. So I just want to leave you this thought. So first of all, we got really lucky because Furstenberg is sort of the only tool, and it's not very, it's very good, but not very quantitative. And in order to do more interesting turbulent systems sort of in a more honest way, well, in any way at all, we know nothing about the Navier-Stokes equations and the limit when u goes to 0. Basically, essentially nothing that isn't a consequence of parabolic regularity. And so, we're missing quantitative tools, but I think that random dynamics is the right path to go down because it doesn't have the pathologies of deterministic dynamics. So I would be very surprised if my great-grandchildren saw a proof of this theorem in a deterministic setting. But for random dynamics, we have at least some hope for proving these universality laws. Okay, that's it.